Exceptions to the octet rule. The octet rule applies mainly to the second period elements. There are 3 categories characterized by an incomplete octet. So you could have an odd number of electrons or more than 8 valence electrons. An incomplete octet would be like hydrogen, who only needs 2 valence electrons to be like helium. Beryllium is actually stable with 4 valence electrons. Boron and aluminum both are stable with 6. Boron is special because it also forms something called a coordinate covalent bond or a dative bond. So this is a compound, or I'm sorry, this is a covalent bond in which one or more atoms donates both electrons that are being shared. Alright, so for example, for BF3, because boron only needs 6 valence electrons, boron gets 3 bonds around it. So if we add up the valence electrons, boron has 3, and each of my fluorines has 7, so that's a total of 24 electrons. So I'd put boron in the middle. 3 fluorines would go around. 2, 4, 6, satisfy the fluorines. 8, 10, 12, 14, 16, 20. Yeah, counted wrong there. So that's all 24. So boron actually doesn't have any valence electrons because, again, it only needs 6. Now, NH3, we would have 8 valence electrons in our picture. So we'd have nitrogen, 3 hydrogens, bond to the nitrogen. That's 6, leaving me with 2 extra valence electrons, so there would be a lone set there. So we're adding these 2 things together. So what happens is the nitrogen shares its 2 valence electrons with the boron. So then we get a structure that looks like this. So the nitrogen is donating both electrons that are being shared, which is what a dative bond is. Now, boron is the only one that does that. So when you're drawing your Lewis structures, watch out for hydrogen, beryllium, boron, and aluminum, because they don't need a full 8 valence electrons to be stable. Now, another problem, or another exception that we have, are odd-numbered electrons. Nitrogen is typically where we see this odd number of electrons. So instead of having all paired electrons, we actually have a single dot for a single electron. They're sometimes referred to as radicals, and they're extremely reactive because of that one electron being by itself. We know electrons like to be in pairs, not alone. So if we look at NO, we would have 11 valence electrons, so that's where we would have our odd number. Nitrogen and oxygen, so they're sharing 1 there, or 2, 4, 6, 8, and then we would have 1. Well, that doesn't really help nitrogen any, so we are going to try and have nitrogen be as close to 8 electrons as possible. So here we have 2, 4, 5, so it's actually going to be a triple bond. So oxygen has a set by itself, and nitrogen only has 1 electron. If we look at NO2, we would have 17 valence electrons this time. So we've used 4, 6, 8, 10, 12, 14, 16, and we would have 1 on the nitrogen. But we do want nitrogen to have as close to 8 as possible. So one of my oxygens is going to be double bonded, and because of resonance, it doesn't matter which one. The other type of exception is when we have an expanded octet, so we have more than 8. Elements in row 3 and beyond can form compounds with more than 8 electrons, and the reason is because they have d orbitals. So we know that the 3rd energy level is the first time that we have access to the d sublevel, so that's why it's row 3 and below. when drawing the Lewis structure, you still want to satisfy all the outer elements first, and then any element that would be in the center. If you end up with extra electrons, those would go on the center. So if we look at SF6, or sulfur hexafluoride, we have 48 electrons to deal with. So sulfur would go in the middle. We would have 6 fluorines coming around. So 2, 4, 6, 8, 10, 12. That takes care of 12 of my electrons, leaving me with 36. We're going to satisfy all of our fluorines. And that takes care of my remaining electrons. So this sulfur doesn't have a lone set of electrons, but it is sharing more than 8. So it has an expanded octet. And the reason sulfur can do that is because sulfur has 3D orbitals, even though it's not using the 3D orbitals when it's by itself. All right, so some more examples. BF2. So beryllium has 2 valence electrons, and then fluorine has 7 each. So that's a total of 16. Beryllium would go in the middle. That takes care of 4 of my electrons, leaving me with 12. Satisfy my fluorines. Beryllium now doesn't need any valence electrons because it's satisfied having an incomplete octet of 4. ASF5. Arsenic has 5 valence electrons, and then each of our fluorines has 7, so that's a total of 40. We'd put arsenic in the middle, and we would have 5 fluorines coming around it. So that's 2, 4, 6, 8, 10, leaving me with 30. Satisfying my fluorines, I've used all 30. So again, arsenic does not have any lone electrons. It has an expanded octet because it has access to d orbitals. Now SF4, we have 34 electrons, sulfur in the middle. So we've used 2, 4, 6, 8, leaving us with 26. Satisfy your fluorines, 2, 4, 6, 8, 10, 12, 14, So that leaves us with 2 electrons. So that means sulfur is going to have a lone pair. So to make room for the lone pair, I'm going to move this fluorine a little bit. And the lone pair would be on the sulfur. And sulfur now has more than 8 valence electrons around it because it can have an expanded octet because it has access to those d orbitals. So one of the forces of attraction that holds covalent compounds together is bond enthalpy. Bond enthalpy is the stability of that molecule. So it's the enthalpy change required to break a particular bond in 1 mole of that gaseous molecule. It takes energy to break a bond, so that energy is released when the bond is formed. Now these bond enthalpy values are on page 401 of your textbook, and they would have to be given to you in the problem. So the total input, how much you have to break the bonds, minus the total energy released, the amount of energy that's formed, is your bond enthalpy, or is your heat of reaction. So BE stands for bond enthalpy, and then the sigma sign stands for the summation. So you can take all the bond energies for your reactants minus all of the bond energies for your products. If the delta H is negative, then the reaction is exothermic. If delta H is positive, then the reaction is endothermic. If the reaction is exothermic, that's telling us that our product molecules are more stable than our reactant. If it's endothermic, then it's telling me that my reactant molecules are more stable than my products. We could also graph this, and so A and B are the graphs. So if I start with reactants at a lower enthalpy and have to go up to a higher enthalpy for my products, this would be endothermic. But if I start with reactants at a higher enthalpy and go down to reactants at a lower enthalpy, that would be exothermic. All right, so let's look at this problem. We have to calculate the enthalpy of reaction, so H2 plus F2 yields 2HF. So if we think about the bonds here, we have a hydrogen and we have a fluorine, and then we have HF twice. So the enthalpy of reaction, would be my products, my reactants minus my products. So I have one hydrogen-hydrogen bond, which has a value of 436.4 kilojoules per mole, plus one FF bond, which has a value of 156.9 kilojoules per mole. So those are my reactants. Then I'm going to subtract my products. Now I have two HF bonds, so we're going to do 2 times HF, which is 568.2 kilojoules per mole. So my delta H value would be a negative 543.1 kilojoules per mole. So this is an exothermic reaction, so HF would likely form anytime hydrogen and fluorine come into contact. Alright, so estimate the enthalpy of reaction using the bond enthalpy values on table 9.4, which is on page 401. So hydrogen would be just one hydrogen bond. C2H4 would look like this. And then C2H6 would look like this. So I would need one hydrogen-hydrogen bond, 436.4 kilojoules per mole, plus, now in this diagram I have 4 hydrogen to carbon bonds. So I'm going to do 4 times hydrogen to carbon, which is 414, plus I have a carbon double bonded to carbon bond. Now, make sure that you realize, or make sure that you take note of, the fact that my carbon double bond, oh, that's the wrong value. I'm sorry, I looked at carbon oxygen. Let me change that. So carbon double bonded to carbon is 620. Alright, so if it was carbon double bonded to oxygen, there's a little footnote to tell you that if it's actually carbon dioxide, it has a separate value than if it's carbon double bonded to oxygen in any other molecule. So those are my reactants. I'm going to subtract my products. Now for products, I have 6 carbon-hydrogen bonds. Plus I have a carbon single bond, so that's 347. Alright, well, because I had hydrogen-carbon bonds on both sides, these 4 here would cancel 2 of the 6 on this side. So I could actually shortcut a little bit and change my math. You don't have to. You can include all of them if you wish. As long as you get the right answer, I don't really care. Alright, so we should end up with a value of, where's my pen? Negative 118.6 kilojoules per mole. So again, it's exothermic. So my product is more stable than the reactants. So calculate the enthalpy of reaction using the standard enthalpies of formation. So this is going back to one of our older units where we do heats of formation. We do products minus reactants when we do heats of formation, so it's a little bit different. So the heats of formation for this reaction would be my product, C2H6, minus my reactants, which is 0 for hydrogen and 52.3 for C2H4. And I would have a value of negative 137 kilojoules per mole. So it is exothermic. So both ways of calculating the heat of reaction for gives you the same outcome in terms of exothermic or endothermic, but our values are different. And that's because the heat of reaction values don't always agree with the heats of formation values, because many times the bond enthalpies because the bond enthalpies are averages instead of exact numbers.